Hello, I would like to introduce our senior design project, Heat Emitting Automatic Temperature Square, or Heat Squared for short. This project is a pavement tile that utilizes sensors to detect snow and ice on the surface and turn on a heating system. Our project consists of 3 electrical engineers and 1 computer engineer. In colder climates, such as the Northeast, snow and ice can be very dangerous conditions to drivers and pedestrians. These conditions will often cause school and businesses to close. Aside from being very dangerous, people will spend a lot of time and money to make these conditions safe again. The DOT uses plows and sand that end up destroying roads and cars. The main motivation behind this project was to create a highly functional device that could be used for pavement that will change the way these colder climate areas handle snow and ice removal. Some of the main objectives for this project are to create a working prototype of the heat square by ensuring that all the subsystems are integrated correctly and work as intended. We would also like to create a smartphone application that interacts with the heat square and allows us to control some of the functionalities such as display sensor data, control the LEDs, and turn on and off the heating system. We also would like to have an indicator LED mounted to the surface of the pavement that will allow us to tell the state of the system. Some of the specifications for this project that we're going to be looking in depth to are how accurate are our sensors. We would like our temperature sensor to be within 3 degrees Fahrenheit of the actual surface temperature of the heat square. And for our humidity sensor, we would like our humidity sensor to read within 10 to 15% of the actual outdoor humidity level. For the heating system, we want to ensure that the heating system is only going to turn on if the sensors provide data of 38 degrees Fahrenheit or less and a humidity level of 25% or greater to let us know if there's moisture in the air. The heating system, we also want to turn off when the surface temperature of the tile reaches 50 degrees Fahrenheit. For the indicator LEDs, we would like them to change with the state of the system. For example, if the heating system is in heating mode, we would like the indicator LED to illuminate red. If the heating system is in the off position and it's just pulling sensor data, we would either like no LED or green LED. And if it's in one of the intermediate states, we would like to have it yellow. We also would like some functionality to override the heating system so that if in the case of an emergency, we could turn it on and off.
This is our hardware block diagram. Now I'm going to try and explain this as linearly as possible. The main function of this project is the heating element. It takes a lot of power to heat a paver to the point that will melt snow and ice. So the voltage input for the heating element is 120 volts from a power outlet. Now, since we want this to be automatic and we don't want to use a manual relay, we will be using a triac relay. This allows for the MCU to send a signal to the relay and tell it to turn on or off depending upon the situation. All of our other devices require a much lower voltage. So we have an AC to DC converter to go from 120 volts to 5 volts. And then we have a DC to DC converter to go from that 5 volts to 3.3 volts. We will discuss those converters in more detail in the later slides. As you can see, the MCU is also connected to the LED, the moisture sensor, and the temperature sensor. It is receiving signals from the moisture sensor and the temperature sensors to determine if the heating element needs to be turned on, and then it is sending a control signal to the LED for control of the LEDs. This is our design schematic for the project. We have not formed our PCB yet, so this is all that we have for now. And as you see in this slide, we have each of our subsystems broken up for easy viewing. And in the following slides, we will go into depth on each subsystem. As noted earlier, an AC to DC converter is needed because everything other than the heating system gets powered by a much lower voltage than 120 volts. Most of our devices are going to get powered by a 5-volt input, so we decided to use a converter that goes directly from 120 volts to 5 volts. This powers the lighting source, the temperature sensor, and the Atmega chip. There's a 15-watt rating for this chip, which is important because the lighting wattage can increase pretty quickly when multiple tiles get connected together. This allows for us to not have such a small limit as only 2 to 3 tiles to connect together. We could connect well over 10 tiles together by having the higher wattage rating. There is only one device that needs a voltage that's smaller than 5 volts, and that is the humidity sensor. And it works best with a 3.3 volt input, so we needed a DC to DC converter that transforms our 5 volt input to a 3.3 volt output. This is an adjustable input slash output chip. The inputs range from 2.5 volts to 6 volts, and the outputs range from 0.8 volts to whatever the voltage input is. The equation shown in this slide is given in the data sheet, and we chose appropriate values as needed to get a 3.3 volt output.
Initially, the idea of this project was to create a green, energy-efficient way to help those in cold, snowy, and icy areas have a way to clean the walkway and driveway with ease. The battery would be used as a rechargeable storage device for additional backup power, while the inverter converts the power to useful AC voltage that home appliances use. In this case, the AC heating element of the heat square. Looking into solar power as a power source, it seemed like a really great idea. However, for the initial cost and integration of the battery, inverter, and the size of the solar panel needed, our group will not implement solar power in this version of the heat square, largely due to the additional expenses that were out of our project budget. In the end, we decided to go with a more universal type of power and make the heat square tile system run off of any 120 volt AC outlet. This connection would have to be able to withstand harsh and wet conditions on both ends of the connection. The purpose of choosing this power source is to give the end user a more consistent and reliable power source without the worry of a drained battery or the worry of a failing battery due to old age, which in turn leads to another benefit that will allow a maintenance-free system. There will be no need to service the batteries, solar panels, inverters, etc. The end product should be a user-friendly device that will turn on when connected to a power source and start to operate correctly with the various sensors to keep the walkway or driveway heated, snow and ice-free. The main power source to power the heating element in the heat square will be controlled by a triac device. This will allow us to safely switch the high voltage from the mains outlet on and off while keeping the rest of the electronics completely isolated from the high voltage. The triac is activated when there is a high logic level on the corresponding I/O pin and deactivated when there is a low logic level on the pin. The microcontroller will send the corresponding signals based on the conditions from the humidity, temperature, and other user app settings to control the triac. The power flow through the PCB and components will be able to safely test and troubleshoot first by doing a voltage drop test. We first verify outlets are providing the correct voltage, then we plug the system in and can test if the corresponding subsystems are receiving the correct voltage supply. If they are not, we can unplug the system from the power source and continue on with a continuity check to verify the resistance level on each component based on the manufacturer's specifications.
For the temperature sensor design, we decided to go with a negative temperature coefficient 3950 precision thermistor. We decided to go with this thermistor because we did some research on resistance temperature detectors, thermocouples, and thermistors, and it turns out that the thermistor has the highest accuracy, the smallest size, one of the best response times, and the susceptibility to noise is very low. This specific thermistor is accurate within plus or minus 1 degree of Fahrenheit, has a range of negative 55 up to 105 degrees Celsius, which is well out of range for this project, and it has an IEC sensor rating of IP68, which is one of the highest ratings you can get for dust and waterproofing, which is perfect for a sensor that's going to be mounted to the surface of outdoor tile. To test this sensor, we intend on connecting it to a breadboard with a pull-up resistor and using an Arduino. We are going to just run some code through it, make sure it gets some temperature readings, compare it to a known good temperature sensor. For the humidity sensor, we decided we would use the DHT11 relative humidity sensor, which is a capacitive humidity sensor. We decided to go with capacitive over resistive or thermal because it was more accurate and had better results. This specific humidity sensor actually utilizes an NTC thermistor on the inside of it, so it's also capable of detecting temperature. It actually uses the temperature to convert to humidity. This humidity sensor has a range from 20% humidity up to 95% humidity, and there can be some errors, so it's only accurate within 5 degrees or 5%. We also decided to go with this one because it operates on 3 to 5 volt power, which would be easy to attain with the microcontroller. For this one, we also intend on connecting it up to a breadboard and plugging it directly through a resistor to the microcontroller. We'll run some code through that and ensure that we're getting accurate humidity sensor data before integrating it with the rest of the system. For the heating system, we would like to use these 120 volt AC current resistance cable, and essentially what we plan on doing is having a relay that goes right before the heating system. The relay will be attached to power from the wall outlet as well as a signal from the microcontroller. When the microcontroller signal is sent to the relay will then apply wall power to the heating system. To test the heating system, we intend on plugging the cable directly into the wall through maybe an extension cord or something like that, and just make sure that it's actually turning on. To ensure that it's turning on, we're going to use an AC current meter around the cable and just ensure that we're actually getting power to it. We also want to test the relay, so to do that we're going to apply the 5 volt signal to the relay and make sure that it opens and closes as intended, and we're also going to make sure that we're able to get the 120 volt AC power on the other side of the relay.
For the lighting portion of this project, we will be using the WS2812B LED as the product. This is an RGB color changing LED strip. The product has 4 ports. VDD is the power supply, D-out is the control data signal output, VSS is the ground, and D-in is the control data signal input. The great thing about this product is that the VDD, VSS, and D-out for each LED closest to the power is connected to the VDD, VSS, and D-in respectively of the next LED in line already. This makes installation super simple because we just need to make 3 connections at the first LED per strip, and that is it. The last thing that makes this product stand out is the fact that each LED in the strip is individually addressable via programming in the MCU. That means that we can change both the color and the dim setting for each LED individually. When designing this schematic, there were a few things that we needed to consider. First was noise on the data input line. The product manufacturer suggests using a 330 ohm resistor to reduce that noise. Also, external voltages do not always produce the smoothest signals, so we are adding a 100 microfarad capacitor between the power supply and the ground to help smooth it out. This is the top view of our structure. It's going to be 12 inches by 12 inches. And the reason we chose 1 square foot is because typically a walkway is at least 3 feet wide, so our product will seamlessly fit into most walkway designs. The 2 main parts of the top of the structure is the plexiglass over top of the LED strip and pavers laying over top a paver base of concrete fines. Wood is also part of the top of the structure, but we'll discuss it more in the next slide. Plexiglass was chosen because it is a transparent product and it is strong enough to withstand the exterior elements. Pavers were chosen because they are also super strong, can withstand the exterior elements, and they're also pretty standard when creating a specialized or high-end walkway. And so we wanted our product to look similar to industry standards. This is the side view of our structure. The sides and bottom of the structure will consist primarily of wood. We are using cedar wood due to the fact that it is readily available for use. It comes in many different sizes and thicknesses, and it is a recommended product by most industry professionals that use wood on a daily basis as a higher end product. In the middle of the structure, we will have the heating element buried within the concrete fines, roughly 3/4 of an inch below the pavers. And then lastly, there will be a small cavity for the electronics to exist in.
This is the software block diagram for the heat square, showing the logic paths to and from the microcontroller to each element. The microcontroller takes inputs from the humidity sensor, temperature sensor, the battery, the phone app, and by extension from the phone app, the user who controls the phone app. Microcontroller sends outputs to the heating element and to the LED strips. Microcontroller logic and functionality. The microcontroller will take inputs from the humidity and temperature sensors and use these inputs to determine if the heating element should be turned on. When the heating element is turned on, the LEDs will change color or turn on depending on the mode and setting. Depending on external conditions, the LEDs and heating element will be sent inputs from the microcontroller. The microcontroller will also be receiving inputs from a mobile application, where a user will be able to manually control some of the features of the device. The main goals for the mobile application will be that the user will be able to turn on the heating element on or off manually and override the automatic functions of the device. The user will be able to manage the LED's on and off status, as well as the color of the LEDs through the mobile application. And this is a diagram showing the data path between the end user and the microcontroller. Communication considerations. In order to communicate between the user's mobile application and the microcontroller within the tile, the user's home Wi-Fi network will be utilized. The user will connect the device to their home network. If a tile is detected through the application, it will be synchronized to the application and be able to control the connected tile. Bluetooth was researched for one of the options to control the device, and after considering how the user would have to manually connect the device each time they wanted to change the setting and turn on or off their Bluetooth, this would end up being quite time-consuming and frankly annoying. The Wi-Fi connectability would allow the user to open the application and change the settings as soon as they're on their home network. This is the design for the front end of the mobile application. So the mobile application will be used more to monitor the device and perform select operations on. It will have toggle switches for the heating element and the LEDs, status indicators for both, and a drop-down menu for the LED color change. The mobile application will also have an indicator to show if the tile is properly connected to the Wi-Fi and to the power source.
The milestones we have set for this project have been kept up to date for Senior Design 1, and we as a group will continue to hold each other accountable to be able to achieve our milestone goals for Senior Design 2. Currently, we are in the process of building a prototype and testing. Once everything works the way we want it to, we will make changes to our PCB design and get it made. Once received, we plan on testing the PCB design and verify that all requirements are met from the prototype. If changes need to be made, we will make the correct changes and redo our PCB design. This should lead us to a solution where we can start to finalize the project around the middle of November, giving the team a break for Thanksgiving. Once we get back, the project will be ready to present to our peers along with the submission of the final report.
This project is being financed by each of us in the group equally. The most expensive portion of the project is the heating element, and this is mostly because it is difficult to find heating cables at the exact size that we need. Other than that, we won't be breaking the bank to build the prototype. However, if this became available to consumers, it would cost a pretty penny because one tile is only 1 square foot, and the average driveway in the US is around 600 square feet. Not saying that the cost for our system is going to be $550 per square feet once we have it designed, but for the prototype, that's about what we're going to come out to.
Lastly, I want to talk about some obstacles and challenges that we as a group may face. First being sourcing the heating system. It was a little challenging because the company only sells large quantities of the heating element. This becomes a problem for both budget and space constraints. We may also have to cut the heating element to size, which may change the resistive values of the element. Externally mounting the humidity sensor might be a challenge because of it not being enclosed with the rest of the system, and values may vary if the sensor is not placed in a proper environment. Surface mounting the temperature sensor will also be a challenge because it will have to be placed on the top of the heat square and will also need to be flush with the surface to decrease the chance of getting stepped on or damaged from regular use. Another challenge we may face is implementing a Wi-Fi module when moving away from the Arduino, and lastly, initially connecting the device to the home Wi-Fi network.